Okay, let's do this example, right? The question says, find I1 in the circuit. Now they're going to give us a circuit diagram. As you can see, they only have the currents labeled. They don't have any resistance or any voltage. And because that is the case, we're going to have to use KCL. That is the only technique we know that is solely dependent on currents. Now the first thing we have to do when we know we're going to use KCL is to identify the essential nodes. So let's begin to identify the essential nodes. Pause the video and see if you can identify them. This is node 1, node 2, node 3, node 4, node 5. So we have 5 essential nodes in this problem. Now that we have identified the essential nodes, it's up to us to see where do we want to begin. Like I said, you can begin anywhere. I like to do a more methodical approach. I'm going to start at the nodes that are between I1 because that is the current they want us to find. So we know this is current I1, so I can either start at node 2 or at node 5. So what I'm going to do is I'm just going to start at node 5. I'm going to write this as KCL at node 5. So the current entering node 5 is going to be 6 milliamps. So 6 milliamps is entering node 5. You can write this as 6 times 10 to the minus 3 plus we have I1 entering node 5. So we have plus I1. And we also have IX entering node 5. So we have the current IX. And we have no current leaving the node, so this equals 0. Now, of course, something's not right here. One of these currents that they gave us is actually drawn wrong. It might be more than one, but for sure, at least one of these currents are drawn wrong. Why? Because there is no current leaving this node. It's not possible to have a node with just current going in. Current must enter a node, but it must also leave a node. So one of these currents are drawn backwards. The only way to find out is to work through the problem, right? Now we have this equation. We have 2 unknowns. So this cannot help us, right? This cannot help us find I1. But what we do know is if we find IX, we have a relationship between I1 and IX to then find for I1. Therefore, it's important that you remember that you found the relationship for I1 and IX. So let's do something else now. So now I'm just going to choose to do a Kirchhoffs current law at node 2. You can do it at any node you like, but I like to do it from the 2 nodes they want us to find the current for. So we did node 5, let's do node 2 now. I'm going to say KCL at node 2. So we have 6 milliamp of current entering this node. So we can write this as 6 milliamps. I'm going to say 6 times 10 to the minus 3. Now we know this current is going this way. So it's leaving the node. This current is also leaving the node. But then we have a current here, right? And they don't label anything here. So now we have to assume the direction of the current. I'm just going to assume the direction of the current to go this way. And I'm going to label this current IA. So now we can write 6 times 10 to the minus 3 equal the total current leaving is going to be I1 plus 2IX plus IA. So as we look at this problem, now we have 3 unknowns, which is definitely more than we bargained for, right? And we don't have what's called a constraint equation to eliminate one of these. So now we're in a situation now where we realize, okay, we have another equation, and this equation has a relationship between I1, IX, and IA. So there's nothing we can do right at this very moment. So now let's just find another Kirchhoffs current law equation at another node. I'm going to choose node 3, right? And the reason why I'm going to choose node 3 is because I know we have this unknown current IA entering node 3, and we also have IX for node 3. Therefore, I'm just going to choose that particular node. So I'm going to come down here. I'm going to say KCL at node 3. The current entering node 3 is going to be just the current IA that we drew. So we have IA equals the current leaving this node is going to be IX and then 4 milliamps. So we're going to have IX plus 4 milliamps, which we can write as 4 times 10 to the minus 3. Now we have this situation where we have IA equals IX plus 4 times 10 to the minus 3. Now this is where we have to be able to see what's happening, right? In this equation, node 2, we have 3 unknowns, right? We have I1, IX, and IA. We just wrote an equation and IA was the subject, right? So now what we can do is we can substitute in the value of IA into this equation to eliminate one of the variables or one of the unknown currents. So let's do that, right? I'm just going to use the nodal equation we just found at node 3, and we're going to substitute that into IA. Therefore, we're going to have 6 times 10 to the minus 3 equals, we have I1 plus 2IX plus IA, right? And we know IA is just going to be IX plus 4 times 10 to the minus 3. So for the sake of space, I'm just going to write 4 milliamps, right? Now, let's start to at least make this problem a little easier to look at. So I'm going to take this 4 milliamp over to the next side. Therefore, we're going to have 6 times 10 to the minus 3 minus 4 times 10 to the minus 3 equals, we have I1. Now, we have 2IX plus IX, which is going to give us 3IX, right? We know 4 milliamp is the same thing as 4 times 10 to the minus 3. That's why I wrote it as 4 milliamp, right? Just for the sake of space. So now we have this. Let's just simplify this a little more. We know this is going to give us 2 times 10 to the minus 3 equals I1 plus 3IX. Now you can continue to go on with this problem, but I think I'm going to stop right there, right? Now the reason is because I have two equations with the relationship with I1 and IX. I have the first equation we wrote, which was the equation at node 5, and I have the second equation, which is the equation at node 2. So let me just manipulate this one, and I'm going to write it as I1 plus IX equals 6 times 10 to the minus 3. And we know this one can be written as I1 plus 3IX equals 2 times 10 to the minus 3. Now maybe you might be able to find an equation for IX. Let me take a quick look. Now when I look at this, I see I have two equations, right? I have this equation and this equation. Because I have two equations, I can just use systems of equations to solve for the unknowns, right? Your teacher might show you simultaneous methods, and they might use the substitution method or the elimination method. But I'm just going to use matrices, right? So let me write this out. We know these are the two equations I'm going to be using. Let me just make a note of it. This is equation 1, right? And this is equation 2. right? So let's set this up as a matrix. We're going to have I1 and IX. I'm just going to write 1, 1 for equation 1. And for this one, we have 1 and 3. So I'm going to write 1 and 3. Now we know the variables are going to be I1 and IX equals, we have 6 times 10 to the minus 3. And we have 2 times 10 to the minus 3. I'm going to take the inverse of this and then multiply it by our answers, right? So we're going to take the inverse of this matrix. So we're going to say A inverse multiplied by B. Now when we put that in our calculators, so when we take the inverse of this matrix, we're going to get 1.5, negative 0.5, negative 0.5, 0.5. And remember, you're going to be multiplying this by matrix B, which is 6 times 10 to the minus 3, 2 times 10 to the minus 3. Okay, now when you do that, you're going to get the answer. I1 therefore equals 8 times 10 to the minus 3, which we can write as I1 equals 8 milliamp. So this is the value of I1. So this is the answer for I1. And IX, right, is going to be negative 2 times 10 to the minus 3, which we know is just going to be IX equals negative 2 milliamps. So these are our two answers that we got, right? Now, I think the question just wanted us to solve for I1. It said, find I1 in the circuit. So we found I1. So that's going to be our answer for that particular problem. I1 is going to equal to 8 milliamps. So that's kind of how you solve this particular question. We found the currents I1 and IX. Now the problem just wanted us to calculate the current I1, which is 8 milliamps. So this is how we were able to solve this problem. It was a lot more intensive and something we might not be used to. But this is pretty much where we're going for the rest of these videos. We're going to have to really be able, especially on a quiz or a test, these are the type of questions you're most likely going to see. These questions are going to be more involved and they're going to want you to think through the question, right? And once you think through the question, you might have the right equations. But if you have trouble with solving systems of equations, sometimes we can make careless mistakes. Even I sometimes make careless mistakes. Because it's just so much numbers and so much going on that I think it's best always to go with the matrix method. This was something I didn't learn in college. And see, the matrix method is something I learned after my circuits class, which I really regretted because I realized the importance of the matrix method. I encourage you to take advantage of the matrix method. I guarantee you it's going to save you time on the exam, it's going to save you heartache, and it's going to make you not frustrated as much and make you focus more on understanding the actual circuit that you have at hand. So this is the end of this video. This is our introduction to not only the matrix method, but this is a perfect type of question that you might see on the exam when talking about Kirchhoffs current law.